Good afternoon. Shortly we will hear an interesting lecture by Professor Dan Oron on quantum-enhanced super-resolution microscopy. This webinar is a part of a webinar series organized by Photonics Israel on various aspects of photonics. Photonics Israel operates within Engineers Association as a cluster of photonics entities. Our mission is to deepen the knowledge in photonics and to encourage cooperation both within Israel and with photonics entities in the world. We are holding weekly webinars on various photonics topics. We invite you to sign up to follow the activities we hold, which are published in our monthly newsletter. Per your request, the newsletter will be delivered to your mail. My name is Shlomo Glaser. I'm the manager of Photonics Israel. With your permission, a few words in Hebrew. דיברנו על זה כבר, וזה כבר הרצאה השישית בנושא, בתחום של הטכנולוגיות הקוונטיות, שכידוע הן נמצאות במחשוב ובתקשורת, ניווט, הצפנה, לייזרים ועוד. ויש צורך הולך וגדל במהנדסים. אנחנו מתכננים, לאחר גמר סדרת ההרצאות האלה, קורס למהנדסים, שיעסוק בצורך, בעקרונות, בשילוב הטכנולוגיות הקוונטיות במערכות, ואתגרי היישום ההנדסיים שיעמדו בפנינו, בפני המהנדסים. אנחנו מאוד נשמח אם אתם במשוב תביאו את העניין שלכם בקורס כזה, ועל גלי התמיכה הזאת אנחנו נפתח את הקורס בשילוב בעזרה של מיטב המומחים פה בארץ, ואנחנו נעביר אותו ברצון רב. אני רוצה לציין עוד כי יש ספר בעברית שהוא מומלץ, והוא נקרא פיזיקה קוונטית מבוא, כתב אותו דוקטור בועז תמיר, ואני יכול להגיד מניסיון אישי, מקריאה בו, שזה ספר מצוין. Professor Dan Oron earned his PhD in physics from Weizmann Institute of Science in 2005. In 2007, Professor Oron joined the Department of Physics of Complex Systems. His research group deals with the interaction between light and matter at nanometer scale, the growth of characterization of nanoparticles, mainly of semiconductors, and the development of super-resolution imaging methods. Professor Oron, the floor is yours.
תודה רבה, שלמה, and hello to everyone. So this is going to be a talk about the use of quantum principles in super-resolution microscopy, which is an emerging topic in bioimaging, and I'll try to keep it as simple as I can, in the sense that no prior knowledge about too much about quantum mechanics is necessary. I'll try to explain the sort of underlying principles. Please feel free to post questions during the talk. I'll try to keep an eye and see whether there are open questions. I think the main message, if there is one, is that quantum sensing, and particularly here in the context of microscopy, is already a reality. And it's not just something for physics labs, for crazy scientists to play around with in their labs. There's actually stuff that can be done in real life with quantum principles. So without further ado, let's start. And I'll start by a rather long introduction to super-resolution microscopy, so as to set the settings for the problem. So optical microscopy in general as a science has a long history. The microscope was invented 500 years ago, give or take. But the more scientific efforts, if you want, the field of bioimaging is a bit younger, still old, but a bit younger. And I would, if you have to trace it to one point, so the one point where people started looking at the microscope sort of as a more quantitative tool to look at biology, I would choose this point. So the publication of this book, Micrographia, by Robert Hooke. Robert Hooke is very, very famous for other things, the Hooke law of springs and other things. But he was actually the first to realize the potential of the optical microscope in observing biological systems. And in this book, published in 1665, he has many, many drawings of things, hand-drawn drawings of things as they look under a microscope. This is an image from that book. This is another image from that book of tissue. And in fact, Robert Hooke coined the term cells for biological cells, because these cells look to him like the cells of Capuchin monks in a monastery. However, at that time, it was not clear whether the fact that the resolution of the optical microscope is limited, so that you can't see really small things, is due to a technical limitation or due to a fundamental limitation. And the understanding that there's a fundamental limitation dates a couple of hundred years later, which a period which can mark, if you want, the dawn of biological microscopy, quantitative biological microscopy, and the microscope as we know it. So in 1873, these three fine gentlemen happened to be in the same place in the same time. You probably don't recognize their images. On the left, you have Ernst Abbe, who is the person who developed basically the concept of diffraction limit. In the center, there's Carl Zeiss, then just an engineer designing optics, but the father of a huge empire, Zeiss GmbH. And on the right is Otto Schott, a glassmaker and glass blower, and again, the father of a very big industry, Schott Arbeitsgruppe. And in 1873, these three people happened to be in Jena, Germany, at the same time. And the period, if you remember, is shortly after James Maxwell developed Maxwell's equations, or finalized Maxwell's equations. And there was the realization that light is really an electromagnetic wave. So what Ernst Abbe did several years later is to apply the laws of propagation of electromagnetic waves to light under conditions of strong focusing by an objective lens. So it's that simple. And the paper goes by, and this is a copy of the English translation from 3 years later, by the very funny name, A Contribution to the Theory of the Microscope and the Nature of Microscopic Vision. It's a very difficult text to read. I mean, today, nobody would have published a paper like this. For example, the famous Abbe resolution formula doesn't appear there. There's actually no formulas in the paper. And if you read through the text, which is very long, at some point you get to this paragraph. And it says, no particles can be resolved, blah, blah, blah. There's a lot of talk because he was very, very German and precise about this. And then after a lot of talk, he gives the formula, dividing the wavelength by the sine of half the angle of the aperture. That's the famous diffraction limit. And half that when the illumination is oblique. So as oblique as the objective will admit. And this basically set the foundation for the realization that the optical microscope is not limited due to technicalities in resolution. It's limited fundamentally because of the wave nature of light. And the resolution barrier is about half the wavelength, give or take, depending on the refractive index of the medium. And now this barrier that Ernst Abbe set in 1873 was achieved very, very quickly thereafter. And that's because Ernst Abbe was a mathematician. He could design optical elements. But he had these two other people, Schott and Zeiss, along with him. And they manufactured objectives, which basically all objectives to date rely on the design developed then by Abbe, Zeiss, and Schott. And because they were so proficient in making the optical elements, they could make objectives which reached very close to the diffraction limit of Abbe with very little aberration. And so you could say that the science of quantitative microscopy was born in 1873 and died very, very closely thereafter because the resolution barrier stated by Abbe was limited. And there was nothing more to do, right? So surprisingly, it took 120 years for people to start challenging the Abbe limit. But they're not challenging the Abbe derivation. The derivation is completely correct. It goes from Maxwell's equations to a mathematical derivation of the resolution. What may be incorrect in this case is the assumptions underlying the Abbe model. So let's look a bit at the assumptions that Abbe used for developing resolution. But for 1 second, let's define resolution, right? So we have an imaging system. We have an object. We generate an image of that in the image plane. And if we have 2 points here, or 2 close objects here, we want to be able to resolve them. That means to be able to say that there are 2 and just 2 and not 1, for example. There are 2 common criteria for this. One is the Rayleigh criterion. If you have 2-point sources here, 2-point objects, and they sort of, if they're separated enough, they're resolved. And if there's any dip still in between the intensity of emitted by the 2, this could be fluorescence or scattering, this is considered resolved. This is already considered unresolved. Of course, this is not a very good definition of what can and can't be resolved, because there's signal to noise issues here. The criterion which I favor a bit better is the Abbe criterion. That's actually the one that Abbe used in his paper. And that's, can you resolve a grating? If you look at a grating from sufficiently far away, it looks, you don't see the black and white stripes. It looks like a gray haze, like these small dots here, which are probably below the screen resolution that you have. So this looks gray. Here you can resolve the stripes. So the finest grating where you can resolve the stripes, that is the limit of resolution. And now, what are the assumptions put into Abbe's model? So Abbe assumed a lot of assumptions. These include linear optics, so no nonlinearity in the fields. Classical fields, of course, quantum mechanics was developed 30 years later, so he could not have known that quantum mechanics exists. A time-independent sample, so the sample doesn't change over time. There's homogeneous illumination. You don't illuminate portions of the sample. And there's no extra information that is given from somewhere else. And it turns out that each of these properties is a loophole through which you can break the diffraction barrier. This is not really surprising, because Abbe developed the diffraction barrier based on these assumptions. However, the realization of this took 120 years. And today there are many, many methods developed to break the diffraction limit. The 2 most famous ones, I'll show those in a second, are Stead and Palmstorm. Those got Stefan Hell, Eric Betzig, and W.E. Murner the Nobel Prize in Chemistry in 2014. Then there's structured illumination, fluctuation imaging, and a variety of other techniques. And each of these can be connected to breaking one of these. For example, Stead, which I'll show in a second, breaks linearity. Palmstorm breaks the time independence. SIM breaks the homogeneous illumination. And you can say that for every other method. But until a few years ago, until basically we went into starting to work on this, there was no realization of breaking the Abbe limit by non-classicality, by quantum mechanics. But of course, Abbe didn't know of quantum mechanics. So we asked ourselves the very simple question, and this started as really something very, very fundamental. Can you use quantum mechanics to break the diffraction limit? Okay, so before going into how we do that, let's first see what the other methods for superresolution are. So the first method, which earned Stefan Hell the Nobel Prize, is called stimulated emission depletion. It's basically based on the notion that you can use light to quench fluorescence. What does that mean? Suppose I have a beam, which is diffraction limited. This is this blue beam, which excites fluorescence in the sample. And now I have a second beam, the orange beam, which is an eraser beam. It erases the fluorescence from the sample. And now I combine this with nonlinearity. I work with this eraser beam, but I increase the intensity of the eraser beam so much that it's saturated. Once the eraser beam becomes saturated, fluorescence can survive only in the vicinity of zeros of this eraser beam. The eraser beam has a donut shape, and it has one single zero at the center. So if you apply both of these beams together, you excite fluorescence in a very, very tiny spot. And then you collect all the fluorescence from the sample, but you know that whatever you collected came from this very small volume. In practice, this was first demonstrated by using stimulated emission as the erasing mechanism. So you excite fluorescence, say, with a green laser. Fluorescence is orange and red. You use a red laser to stimulate emission into the red laser beam, but backscattered fluorescence is sort of erased. And so you only measure the orange fluorescence. And in principle, this is not limited by diffraction. The more you can saturate the eraser beam, the better your resolution. Then it has some problems. It's a scanning method, so it's slow. There's issues with photo bleaching, and it's difficult to maintain a zero in a sample where there's scattering. But still, this is the first demonstration of breaking the diffraction limit. The second method, Palmstorm, developed more or less at the same time by Eric Betzig and by Xiaowei Zhuang, is based on a completely different principle. So optics is very good at measuring centroids. And if you have, say, a light source and it's diffraction limited, you can't resolve the light source, but you have sufficiently good signal to noise in your imaging, right? What you see on your camera is a circular spot. And if your signal to noise is sufficiently good, you can say that the emitter is localized at the center of this spot. So you have prior information. You know that there's a single emitter, and then you can localize it very well to the center of the spot, the center of the diffraction limited spot. If you want, you see something which looks like a Gaussian, you can mark the center of the Gaussian. However, in order to do this, you need the emitters to be single emitters. But in general, in a biological sample, fluorescent dyes are not sparse. So you don't see single emitters, you see many, many emitters. And that's the kind of picture you see. So Palmstorm use emitters that can be activated and deactivated by light. Usually, these are molecules where there's a carbon-carbon double bond, and you can induce a rotation. This is trans photoisomerization. And this photoisomerization changes the fluorescence quantum yield from something very low to something very high. So what is the idea? You start with your sample, you turn off all the fluorescence, then you turn on only a very, very small fraction of the particles, of the emitters. You measure their positions. You can do this very accurately because they are single emitters. Each of them, in each diffraction limited spot, you have a lot less than one emitter. You mark X's at the centers, and then you quench them all back. You sort of push them back to the dark state. And then you repeat this again and again and again. If you repeat this maybe 10,000 times, you will have sampled almost all the fluorescent molecules in the sample. And now your image is just the X's, right? You marked an X, so the position of the X's within the noise. And so out of this image, you can get this image, which is really nicely resolved. Typical resolutions achieved by this method can go as low as 20 or 30 nanometers. And now I'll show a third method because it's related. It's not that commonly used, but because it's related to what I'm going to show you later. And it's called stochastic superresolution optical fluctuation imaging. Basically, it's the same idea as storm. You have emitters which turn on and off, but now they do this spontaneously. And if you look at the fluorescence image of single molecules, they always blink on and off. They switch spontaneously on and off. So this is something that happens naturally. You don't have to induce it. And now the intensity of a single emitter is not correlated. The fluctuations in intensity are not correlated between neighboring emitters. No matter how close they are, they sort of fluctuate independently. So if you look at the correlation signal, not at the intensity, but at the correlation signal between neighboring pixels in your camera, then there's spatial information encoded in that. And the higher order correlations encode higher spatial resolution information. So this was developed by Jörg Enderlein and Shimon Weiss back 10 years ago. And I'll get back to this kind of method soon. Okay, so now let's talk for a few seconds about quantum mechanics. where did quantum mechanical sensing already show benefit in the context of optical microscopy? So in general, quantum states of light have shown benefit in measuring phase or distance. And even the LIGO, the stellar interferometer that a lot of us have heard about that can measure gravitational waves, that interferometer uses quantum mechanics in order to improve the assessment of, in this case, a distance measurement. So how does that happen? You take an interferometer, in this case, a Mach-Zehnder interferometer. You want to measure this phase, phi. Right? There's two channels, channel A and channel B. And how do you do this usually? Well, you shine light in, and if the intensity the intensity here at the output depends on the cosine squared of this phase, right? The phase difference between these two. If you send more and more light in there, of course, a single photon can only go either this path or this path. And there's an intensity, of course, there's an intensity noise here at the detector. If you want to estimate this phi, it's easy to show that because of shot noise, your phase estimation goes like 1 over the square root of the number of photons that you send into the interferometer. However, the Heisenberg, the quantum limit, Heisenberg uncertainty limit, is 1 over n. So if you send in n photons, you should get 1 over n better, not 1 over square root of n better, somehow. And here, in this case, there's a clear way to do this. For example, consider a state of light, which is quantum, which is called a noon state, n0 plus 0 n state. If you have the ability to send either n photons through channel A and 0 through B, or n photons through channel B and 0 through channel A, and then detect all those n photons here at the output, well, then this state undergoes a phase which is n times phi, exactly n times phi. It's as if the state is composed not of n photons, but of one photon, which has n times shorter wavelength. And this, of course, gets you the higher resolution. It's cosine squared n phi, and hence you can reach the Heisenberg limit. And in fact, there's a very, very nice demonstration of this. I'll show it in a second from the group of Oron Zilberberg several years ago. Of course, it's a hard problem. It requires quantum state generation and quantum state detection. But this was used in polarization microscopy. So I'm not going to tell you how this noon state is generated and not exactly how it's detected. The whole point in what I'm going to show here is that if you now look at the noise in this relative phase measurement from 50 single photons, 25 photon pairs, or 17 photon triplets, all corresponding to 50 photons, give or take, you'll see that this phase estimation is noisier than this and is noisier than this. And of course, the real thing you can measure with high intensity. So all this triplet third order correlation signal is much closer to this. But of course, this is not practical because the generation is really tough and the detection is really tough. So by the time these 17 triplets have passed through your sample, about 1 million single photons pass through the sample. So it just doesn't really give you anything. What about other quantum resources? So now I'm getting to the main part of my talk, and this is the outline. I'm going to use a different resource, not correlated photons, entangled photon pairs, but rather the fact that you have anti-bunching or quantum effects on the photon statistics. So I'll explain what quantum emitters are and then what anti-bunching is and how it can serve as a poor man's quantum resource in imaging. And then I'll probably not have time for this second topic. I'll talk about quantum super-resolution microscopy via photon correlations. And then I'll talk about our more recent work on quantum-assisted confocal imaging, where I can show you biological images which are enhanced from quantum principles. Okay, so most fluorescent markers used in biology, actually most light sources, quantum light sources, are quantum emitters. What does a quantum emitter mean? A quantum emitter is an emitter that can only emit one photon at a time. This makes a lot of sense. Consider, say, a dye molecule. If it's in the excited state, it can emit a photon. But if it emitted a photon, that means it's in the ground state. If it's in the ground state, it takes a time to be re-excited. And from the ground state, it cannot emit a second photon, right? So a quantum emitter can only emit one photon at a time. How do you detect this? You send the stream of photons from the quantum emitter into this very, very simple setup called the Hanbury-Brown Twiss interferometer. You have a 50-50 beam splitter here and two single photon detectors. And if this is truly a quantum emitter, and each detector clicks when it sees a photon, these two detectors will never click simultaneously. Why? Because a photon has to choose. It either goes here or here, and the emitter can't emit two photons at the same time. So either this sees a 1 and this sees a 0, or vice versa, or of course both can see zeros, but never two ones. If you plot the correlation between the time trace of ones and zeros seen by this photon, by this detector, and by this detector, it looks like this. There's basically no correlation. And then at zero delay, you see a dip in the correlation, which goes all the way down to 0 and then goes back up, right? So this is called anti-bunching, and this is the resource we'll use, and it's abundant. Any fluorescent molecule, any quantum dot, any nitrogen vacancy center atom, give me an emitter, usually that emits anti-bunched light. You can think of this as a kind of correlation, right? What is anti-bunching? If you're sitting down at the pool and you're looking at kids going down that slide, you see that they go down into the pool one at a time. This is because there's some process here, in this case, this bouncer, which doesn't let two kids go simultaneously on the slide. And this intensity correlation, if you correlate the arrival times of kids to the pool, you'll see a dip at 0 delay. If you see a kid down at the pool now, you know that there will be a few seconds when no other kid will enter the pool. There are other kinds of statistics like bunching. This is a bouncer and he's letting people into the pub, and you don't go to the pub alone, you go with your friends. So if you're an observer standing inside and you see somebody coming in, it's more likely that they're not alone. Somebody else will follow them. This is called bunching. And this is the effect that was used by Hanbury, Brown, and Twiss in their stellar interferometer way back in the 50s. And measuring this is very, very easy. We usually do this in a pulsed manner. So you excite your quantum system with pulses, and then you measure correlations. And at 0 delay, you have a dip in correlations. And now the photon stream from a quantum emitter is more uniformly distributed in time. If you consider how many photons arrived in a unit time, you will see that the number of photons is, the noise around the mean number of photons is less than shot noise limited. And this is why it's really inherently a quantum effect, because you're beating shot noise. Okay, how can you use this in order to increase resolution? So I'll show a mathematical slide. If you don't get it, never mind. I'll show a very intuitive slide in a second. So a classical emitter emits a Poissonian photon number distribution, which means the variance of the number of photons in a unit time measured by the detector equals the mean. However, for fluorescence, you can do the math, and there are reduced quantum fluctuations. The variance is less than the mean, so it's less than shot noise. The distribution of the number of photons per unit time is less. And this is exactly the signal we're going to look. We're going to measure the signal, which I define as the anti-bunching signal, which is the classically expected variance minus the measured variance. And it can be shown that this is proportional to the probability of detecting a photon squared. Hence, if the probability of detecting a photon depends on space, right? It's a point spread function. A Gaussian squared is narrower than a Gaussian, and you have a better resolution. But there's a more intuitive explanation to this. Maybe I'll skip this. The more intuitive explanation was given by Stefan Hell, the winner of the Nobel Prize in 1995, same year that he developed STED. And he said the following thought experiment. So it's a Gedanken experiment. Suppose we have an emitter which always emits photons in pairs, and we can detect pairs. Can we get a better resolution? And the answer is yes. How do you do this? It's basically a Hambry-Brown twist interferometer. You construct this 50-50 beam splitter and two cameras, and now you only look at cases where one photon hit one camera and the other photon hit the other camera. Now, this photon, because there's a diffraction limit, it gives an estimate of the position of the emitter within the diffraction limit. And this photon also gives an estimate of the position of this emitter. But these two estimates are independent. If you have two independent estimates of the same variable, you actually have a better assessment, in this case by a factor of square root of 2 of the position. So you really get a better resolution. Of course, there are no such emitters. There's no fluorescent molecule that always emits photons in pairs. However, there are many, many molecules which never emit photons in pairs. This is called antibunching. And both of these cases represent a deviation from a Poisson distribution. So if you use that deviation from a Poisson distribution, there's extra spatial information. But instead of looking at pairs, we can look at the missing pairs, the pairs that aren't there, which is exactly this antibunching signal. And I note that we can look also at third order and fourth order antibunching, because there are not just never pairs, there's never trios of photons emitted simultaneously, et cetera, et cetera. Now the signal becomes weaker and weaker as you go to higher orders, but it might be still observable. Okay, so how do you run an experiment to measure this? The experiment is actually very simple. You need a single photon sensitive camera, right? And you need to be able to measure single photons from your sample, but these cameras are typically slow, right? The frame rate is maybe 1 kilohertz, so 1,000 frames per second, which means you have to excite your sample only 1,000 times a second. So you use a 1 kilohertz laser, and you have to make sure that the pulses are sufficiently short so that they're much, much shorter than the radiative decay lifetime of the emitters. So they can't re-excite, you can't emit and re-excite. So we use quantum dots. They have a lifetime of tens of nanoseconds and a 300 picosecond pulse, so we're okay. And that's basically it. Take this, grab a frame in the single photon sensitive camera for every pulse, do statistical analysis on this frame, and there you go, you have super resolution. What kind of statistical analysis do we do? We make sure that every diffraction limited spot is imaged onto 4 camera pixels, so a square, a 2 by 2 square, and then we measure correlations between pixels in this square. So these two, the diagonal pairs, and indeed you can see this anti-bunching. And you can also measure third order correlations between triplets of detectors within this diffraction limited volume. The anti-bunching then looks like this, right? But you see less correlations in the center pixel. So when all 3 photons arrive simultaneously. And to make a long story short, this is the end result. This is the integrated intensity. So this is the fluorescence signal. This is the anti-bunching signal. And this is the third order anti-bunching signal from a sample of semiconductor nanocrystals just dispersed on a piece of glass. So you see the resolution gets better from here to here to here. For example, look at these barely resolved dots here. They're much better resolved. Here you can actually see that there are 3. So that works. However, it's completely impractical. Why? Because here we have about several hundreds of thousands of detections. Here we have a few hundreds. Here we have about 10 detections. And to take this data, the camera had to be on for an hour because we operate just at 1 kilohertz. So we basically get very, very low signal. So we can't really do anything practical with this. We need a fast camera which can resolve single photons. And until recently, there hasn't been a technology that can do this, to be both fast and single photon sensitive. So these are electron multiplying CCDs. They are single photon sensitive, but they're very slow. And when we started looking at this, I'll skip something here. When we started looking at this, there was no available technology that could do this, so we had to develop something ourselves. And this is our version, our take on a single photon sensitive camera. Take a fiber bundle, so it's a bundle of many, many multimode fibers, and couple each of these into an Avalanche photodiode, which is a single photon sensitive detector. So each of these is a pixel, and now each of them is connected to a single photon detector, which is, it's just an expensive device, a few thousands of dollars. And take all this data and use a correlator, so an electronic readout mechanism, to basically give you all the photon arrival times. So you have all the photon arrival times, and whenever a photon hits this, you get both the position through which of the detectors got it, and also the time of arrival, because these are relatively fast detectors, so maybe 50 megahertz response. Problem is, each detector is a few thousands of dollars, so you can't really have many pixels. So we have an effective camera with 15 pixels, 16 channel correlator, and 15 pixels and one trigger, basically. And that can cover whatever you want, one diffraction limited spot or a few diffraction limited spots. The time resolution is nanosecond. The single photon sensitivity is ensured. And you can measure simultaneously photon correlations across this image, but it's a very small image. So now what can you do with this? And in order to take advantage of this, what you need to do is to take an imaging modality which inherently uses a small detector or doesn't need much of a size of the detector. And the candidate is something called image scanning confocal microscopy. What is confocal microscopy? In a confocal microscope, you shine, it's a laser scanning microscope. It's a classical instrument invented in 1957 by Marvin Minsky. You illuminate one point in your sample, measure the fluorescence from that point. And in order to reject out of focus background, you image this point here onto a pinhole. And only light that passes through the pinhole gets to your detector, a camera, or just a photomultiplier. And now, out of focus light is not imaged well onto the pinhole rejects most of it. So it gives you very nice Z resolution in scattering media. And that was the reason that people used the confocal microscope for the past 50, 60 years. But now, if you choose to close this pinhole very, very tightly, such that it transmits only a few percent of the light, you also gain in resolution in XY. But no biologist actually does this. They don't do it because it's wasteful, right? You're rejecting most of the light, and you're bleaching the fluorescence in the sample. You're exposing your sample to a high load of photons, which doesn't make sense. Now, 10 years ago, people came up with this very nice idea. Instead of using a small pinhole, let's use a small pixelated detector where the size of each detector pixel is the size of a small pinhole, but the whole thing covers the area here. And now you collect all the fluorescence, but each detector is essentially a small pinhole, which makes sense, right? But now you don't just integrate the signal over all these detectors. You have to do a small manipulation of the signal, which is called pixel reassignment. Why is that? Each pixel sees the sample with a slight parallax, a slightly different angle. And that means the image on each detector is slightly shifted. So in order to get the extra resolution, you first have to shift the images and then sum them up. But once you do that, and then you can do some deconvolution, some deconvolution in Fourier space, basically taking account of the fact that higher frequencies in Fourier space are attenuated more in this kind of a microscope, you can get an up to 2-factor of increase in resolution. And this is already a commercial instrument, bite size. It's called an ARIScan or image scanning microscope. But now, what can we do with quantum correlations now? We can actually look at the same thing, but now consider each emitter as a source of missing photon pairs, just like I showed you before. So now we're going to look at this anti-bunching signal in addition to the intensity signal. And this is really the difference in the area of this 0 delay orange peak with a 1 pulse or 2 pulse delay yellowish peak here. So now we have our excitation and detection point spread functions. This is exaggerated, of course. The confocal excitation is centered here. The detectors are centered here. X1, X2, and X3 are detectors. The image scanning microscope gives you a point spread function which is halfway between the excitation and the detection. But now if you look at photon pairs, you get a point spread function which is a multiplication of 2 image scanning microscopy point spread functions, right? These multiply these 2 green Gaussians, which are already narrower than what you would get with a confocal, and place that in between these 2. So now you have to take all these correlation images between every pair of detectors, shift them correctly, and sum them up. And that should give an enhanced resolution. So let's look at a very simple sample of 2 semiconductor nanocrystals. This is how they look in a confocal microscope. That's how they look in an ISM microscope, just using the intensity. That's if you deconvolve or Fourier weight. And this is using the quantum correlations. You see the resolution is more or less the same as here, a factor of 2 better. And then you can deconvolve this and get a resolution which is roughly a factor of 3 better than your confocal. Moreover, you can get a better Z resolution. So because this is a process which involves 2 excitations and 2 detections, it's more sensitive to deviations in Z, because as the density of photons goes down in the excitation, right? You're exciting with a focused beam, the higher order processes are attenuated more. So this gives about twice the resolution of a confocal microscope in Z. And this is an example of a bioimage. So these are microtubules labeled with quantum dots, as seen in a confocal microscope, in an ISM microscope, and in a quantum ISM microscope. So this is just a quantum version of ISM. You can see the enhancement in resolution. You can also see the loss in signal, right? The signal intensity is lower because correlations take more time to accumulate. In the maybe 3-4 minutes I have left, let me just show you a few things which we are working on now. The first is to use something which is much better than this very, very funny fiber bundle-based detectors that we've been using. So in the past few years, we've been collaborating with a group that makes monolithic arrays, CMOS-compatible arrays of single photon Avalanche photodiodes. This is a 23 detector array manufactured by our Swiss collaborators, actually made in Israel, I think, in Tower Semiconductor, but designed by our Swiss collaborators. There's issues in using this for quantum measurement because there's crosstalk between these pixels, because it's a monolithic device. The distances between the Avalanche photodiodes are very small. However, we've shown that you can use this for quantum image scanning microscopy. So doing what I described now is possible with this. And now instead of this 100K detector with fiber bundles, we have a less than $10,000 chip with an FPGA that does basically the same thing. The other thing we're doing is to do algorithmic augmentation of the signal. And the issue is, as I showed, it takes time to accumulate enough correlation signal to get the resolution. And the question is, do we actually have to accumulate sufficient time to have a very good SNR in the correlation signal? And the answer is no. We can take a correlation signal, which is noisy, but remember that we have an intensity signal, which is very not noisy because we have a lot of photons there, but low resolution. And now we can algorithmically merge the high resolution noisy image with a low resolution but very low noise image. And this is something we demonstrate here. So this is an ISM image of a variety of a sample with many quantum dots on a surface. This is the noisy quantum image. You can't extract much of this. And this is an SEM image, an electron microscope, where each of these white dots is a quantum dot. And now you can reconstruct this image alone and get a rather crappy image. You can reconstruct this image alone and get an image with spurious, erroneous localizations because it's very noisy. But you can use the information from both and get something which is very, very close to reality. And finally, I want to say that these fluctuations don't have to be quantum. Quantum fluctuations have advantages. Classical fluctuations have other advantages. You can use either of them or both of them together to get enhanced resolution, which is another thing we've demonstrated. So things we're working on now are imaging with organic dyes in biological systems. This makes things a bit harder because you have to be able to match with the biology, and also better reconstruction algorithms because we still haven't used everything that, all the armor, all the ammunition that we have. But just to show you, this is an image and this is the reconstruction. And we know that this image is of pairs of fluorescent molecules. So you really see here, in this case, 60 to 80 nanometer resolution in a standard confocal microscope working at red wavelengths, so 650 nanometers. So the resolution here is give or take lambda over 8, which is, yeah, it's not bad. So with that, this is my summary. Before summarizing, I just want to acknowledge all the people who did the work here. Some excellent students, especially Osip Schwartz and Ron Tene, and more recently, Uri Rossman and Gur Lubin, collaborations with Radek Lapkiewicz in Warsaw on the technique, and with Michel, Claudio, and Eduardo from EPFL on the spat arrays, with Yonina Eldar on algorithms, with Efrat Shema on biological samples, and with Yaron Silberberg, who unfortunately passed away a couple of years ago and is dearly missed. So this is my summary, and I'd be happy to take questions.
Right, thank you very much, Professor Oron. It's now it's time for your question, please. I have a question for you, Professor Oron. You show some set in the lab with mirrors and other elements. Are they in the play? May reduce the resolution?
So in fact, we don't use mirrors. In fact, we just use, we don't use beam splitters at all. Beam splitters are here just to sort of demonstrate the effect, how the effect is measured. In practice, our beam splitter is just diffraction. We sample our image with a detector that is single photon sensitive, but such that many detectors, maybe 5 to 15 detectors, sample a single diffraction limited spot. And so we use diffraction as a beam splitter. So there's actually no beam splitters used in this setup.
And regarding to the pixels, you show in one of your slides many pixels that you use both at the same time, but they have some difference in their characteristics, in the performances.
You mean here?
Yeah.
Yes, this is a plague of avalanche photodiode arrays. Not all avalanche photodiodes in an array are made equal. Some of them, like this one, have higher noise characteristics. That's what you see here. So when you image this, you see hot pixels or hot detectors which have more dark counts. The reason you actually see this is because an avalanche photodiode emits light when it fires. So it emits light whenever there's an avalanche, and even if there's no photon, if it's a dark count, it emits light. Generally speaking, today, these CMOS compatible APD arrays give quite uniform responses.
Okay.
Okay, there was a question about non-fluorescent inorganic samples. So that's a very good question. Most of biological imaging relies on fluorescence, and as such, most of the tools were developed for fluorescent samples. However, these tools, which are based on something like image scanning microscopy, can be applied also to scattering, but it's a bit more complicated because in scattering you also have to take into account, because scattering is a coherent process, you also have to take into account the phase. So you need to establish a phase-sensitive spatial detection method. And in fact, this is something we're currently working on. There hasn't been a good realization of super resolution in coherent scattering to date, but I can tell you that we actually have a setup working in the lab. So I hope to be able to tell you something about this quite soon. So there's hope there, but the resolution enhancement is not amazing. It's a factor of 2 to 3, but it's still something.
Right. Gilad Laredo, I have a question for you.
Yeah, this is the question that I answered. That's the question that I answered.
All right. Okay, and are there more questions? Let me see. No, I don't think so. So I would like to thank you again, and maybe in the future we'll ask you to provide us more about your work.
Wait, there was another question here.
Okay.
How do you define the shot noise limit in the context of anti-bunching microscopy? So classical light would emit light in pairs. If you look at a laser, for example, this is classical light, and you may use a Hanbury Brown twist setup. Sometimes both detectors would click. That's because in the Fock basis, is the basis of the number of photons per unit time, you have a Poisson distribution, which means sometimes 0, sometimes 1, sometimes 2, etc. However, defining the shot noise in the context of anti-bunching microscopy is a bit tricky. You can find the derivation in the paper, and I could say something more about this, but it's a bit tricky because it's a dark signal on a bright background, and the noise is not shot noise of the signal itself, it's the shot noise of the background. But yeah, it's a bit more complicated, and in fact, this is what limits this technique's practicality to second-order correlations. But we have a full derivation of this.
Okay, let's see if we have more. You have a hello from Germany that I see. Okay. Well, I don't see any more. So thank you again.
Thank you, Shlomo, and thanks for all of you for sticking up and listening.
Okay. Goodbye.
Goodbye.